Well, welcome back. This is part 2 of the Target Radar Cross-Section lecture. That's lecture 4 of the Introduction to Radar Systems course. Now let's look at what contributes to the radar cross-section. What are the scattering mechanisms that there are? And how do they contribute? Here we've got just a generic air-breathing vehicle, I'll call it. And it's got all kinds of stuff on it that you'll find on most things that fly in the air. Some objects that radars see have fewer, but this has got them all. And it's a good example. And probably not many have all of this stuff. But it's a great way to look at physically what are all the different things that can cause backscatter. Okay? And then we're going to get into the physics of what's going on a little later. This is, you look at the object and what does it. Okay? And if you look functionally, they divide up into 3 areas. You can get backscatter from the structural system. The vehicle or the target can have wings, control surfaces that help you to fly and turn your aircraft. Okay? It's got its body shape. It could have a blunt nose, a round nose, a tipped nose. It could have a circular or a triangular cylindrical shape. It could be square. There are control surfaces like the elevators on the backs of wings. That's the structural stuff. Then there's the stuff that gets you from here to there, the propulsion. You've either got propellers and engines, or you've got an inlet where you're going to let air in for a jet or a ramjet or a okay. And you've got, if something is looking at the back, you've got a tail end where you'll have exhaust coming, an exhaust port. Okay. And then we've got avionics, stuff that helps us get from here to there. We could have a seeker, which is a sensor, which, well, it wouldn't be covered by metal here. There'd have to be an opening for an antenna for either an infrared or a radar system, and the radar energy can get in there and scatter back. So we've got that. We've got antennas for maybe a GPS system on the air vehicle, or communications. It could have an altimeter if it's a single-engine aircraft and little wire sticking up. That's going to be the altimeter wire and stuff that sends a beam down to the ground. So you can have fasteners that connect one stage of a missile to another. You can have the shape of the missile be a cone and then go to a cylinder, so there's a discontinuity. There can be grooves where the stagings begin and end. Every one of those things that I talked about, when that plane electromagnetic wave hits it, it's going to interact with it. And what's going to happen is we've got to satisfy this stuff called Maxwell's equations. And now's probably the best time to bring it up. And that is, back in the 1800s, there's this guy named James Maxwell. I just have over here I can just see it from where I'm looking. I have 2 copies of copies. You know, they were printed in 1960 of his 2 volumes where he described the theory of electricity and magnetism. And he came out with a set of equations which link up how electromagnetism works, the theory of how that stuff works. And that the electric energy is coupled to the magnetic energy. And whenever you have the interaction, particularly of an electromagnetic wave and metal, this metal object, you have to satisfy Maxwell's equations. And that satisfying of Maxwell's equations was what causes the reflection. And so what we've got to do is solve Maxwell's equations when this electromagnetic wave hits this beast. And there are all kinds of things that happen. Now the first thing is that, and it's probably the easiest way to see it. We're going to talk about it later, but I want to just bring it up. Sometimes it's nice to tell you again, and then remind you what I told you when I'm coming through with a concept. Maxwell's equations tell you such things as you can't have an electric field inside a metal. But when you come up to this metal and this moving electric field hits it, in order to satisfy Maxwell's equations, you generate currents on the surface of the target. And to cancel, and those currents create, those induced currents, they're called, create fields in the opposite direction so that on the surface of the metal, in the metal itself, you don't have electric fields because you can't. So that Maxwell's equations are satisfied is a nice way of saying it. And so these induced currents generate themselves electromagnetic waves, and they're the reflections that you see back. But you've got this very complex object with all these things going on, and the electric fields, electromagnetic wave interacts with all of these different body shapes, control surfaces, inlets, exhausts, seeker ports, fasteners, differently, and they all add up together, and they give you the sum total of the electromagnetic energy back. So what you're going to see is there's a huge volume of knowledge in mathematical engineering and physics that has gone into understanding how to do these calculations. And we'll get into them later. But the point is, what we got to do is we got to satisfy the laws of physics, Maxwell's equations, to get. That's the big picture. Now, let's move on, and we're going to move on nice and slowly so you see what's happening. When I give you an idea, I'm going to show you some movies now on the interaction of simple electromagnetic wave with simple objects to show you these different effects. Now, I've explained to you physically like what they are on top of for that preceding air vehicle. But you can break down really into three categories, the kind of interactions that you have. The first one is you hit a flat surface, like when light hits a mirror, and it reflects right back. And we're going to look at the case. The first case is when a specular reflection, when an electromagnetic wave, and we're just going to look at the electric field part of it. It hits a flat plate, and it bounces. We're going to have other effects we'll look at, but the main effect it's an example of is specular reflection. If you have an electric wave, it hits the plate, and here the electric field, this X means the electric field is in the down direction, the magnetic field is going in this direction, and the direction of propagation you'll see in the movie is going in that direction. It's going to bounce back. We're also going to see diffraction effects, and I'll talk about them. The next case is when the same kind of an electric field comes in at an angle, and from your feelings about light, you're going to have a wave coming off, bouncing off. But also you're going to have the wave propagate down the path. Particularly the first part of the wave is going to hit right here, and you're going to see what we call leading edge diffraction. That is, at the leading edge of a wing, you're going to get a reflection. Then when we change the polarization, the wave will go down, and you'll have, at the end of the wing, a trailing edge reflection. Then we're going to look at a cylinder, and when the wave hits it, we're going to see a specula coming off the cylinder. But if we change the polarization, we're going to have the creeping wave come around. Okay? And you're going to see that creeping wave effect. And then lastly, when we send a wave into a cavity, like a rocket motor or a cockpit, or roughly speaking, or the inlet, it's a very good reflector. And if the energy goes in, unless you have a lot in here to absorb it, energy's going to come out. And one of the properties that you end up getting is an entity called a standing wave, where there'll be energy that will just stay there, but energy will be reflected back and you'll see it. So I'm going to go through these one at a time. I'm going to show you videos that last maybe 10 seconds or so, and I can click on them again and you can see them and we'll talk about them. Let's look at the first case. The first case, the phenomena we're going to look at is specular reflection. Okay? Now, these have all been generated with a calculational technique known as finite difference time domain simulation. So it's a way of propagating electromagnetic waves and having them interact with conductors and things like this. That's very simple. And it's scattering by a strip. It's a Gaussian pulse that's incident on this strip, 4 meters long, and the width of the electromagnetic pulse is 0.5 meter. And the E-field polarization is in the Y direction, going into the screen that you're looking at. And the phenomena we're going to look at is specular reflection. And here's what you're going to see. The red is positive and the blue is negative. And this is what it's going to look like in time sequence of photographs. You're going to see the wave come in. When it gets to the strip, it's going to create those induced currents in the opposite direction, which will create opposite electric fields. And you'll see the field go back out, and that's the reflected wave going out. Okay? But also you see energy coming off the rear. And we'll talk about that later. Okay, now let's go, and as if I click on it, here you'll see the movie. It takes its time, but it comes in. And here's the electromagnetic wave coming in. And now watch what happens when it hits the metal strip. Can't have an electric field in here, so we have to generate some induced currents. They're induced. Bingo! They generate an electromagnetic field. Okay? And that's the reflected specular. But notice that some of the energy is behind it. That's that in the propagation lecture we talked about diffraction. How some of the energy can go behind an object. I'm going to go through this one more time so you can see that, see the diffraction where it's going behind the object. Okay, let's do it one more time. Now this time I want you to focus that the red, the energy, not only comes by it as you'd expect if it were light, but and the wavelengths weren't the size of the object. You're going to see some of this red energy go behind here. And that could be like energy going behind a hill. If the radar beam hit the hill, this was all perpendicular. If that plate were perpendicular up and down, there's energy behind it. And that's called diffraction, where the electromagnetic beam bends around it. Okay? Now we're going to look at leading edge diffraction, where the beam comes in and will hit this leading edge and will generate a backscatter at this leading edge. And you can see the beam coming in, hits it, and creates. And also you have the reflected beam up here too, as you'd expect as it hits. Okay? But coming in the direction of where you were, you'd have the radar back up here. This is the leading edge diffraction that will come back to you. Okay, now let's look at the beam come in. And this is the leading edge diffraction. Bingo! The energy will come back, but also we've got this reflection right back here, where the beam reflects off, but at an opposite sign of the electromagnetic field. And we also see very little interaction at the back. To let you know how this is the polarization dependent, that's where we had the polarization going in one direction. Now when we change the polarization, we'll get trailing edge diffraction. Now a lot of radars use radiation that's a mixture of linear polarization. Excuse me, the best way to say this is, what you saw was a radar that was linearly polarized and exactly perpendicular the electric field was to the plane. It was vertically polarized, perfectly relative to the wing surface. If the plane had been diving a little bit, you'd have a little bit of each kind of relative polarization, and you'd get some leading edge and trailing edge, which you'd get most of the time. But now when we have the magnetic field coming out and the electric field in this direction. Okay, now we'll see what happens. And we'll see we're going to get at the trailing edge. We'll get the deflection. We'll get the diffraction. We'll get the reflection back from the trailing edge diffraction. You see a little bit of leading edge, and here we see the behind the plate we see energy, and at the tip we see energy coming back to the radar. Interesting. So we see the electromagnetic energy does not stop by the barrier, it continues on, and that's diffraction around the plate. Okay? Now let's look at specular reflection when we send an electric field that's along the line of an infinite. It's a long, tall cylinder. And here's what we see. We see again a specular reflection going back to where the radar beam came from. And this again is for one polarization. We'll get the specular, and if we change the orientation of the electric and the magnetic field, we're going to get a different phenomena. What we saw just there was a specular coming back towards the radar. Okay, let's look at it again. Have the electromagnetic wave coming in, and we want on the cylinder the zero current, and we generate the wave coming back. That's an example of specular reflection. Okay. Now if we take an example where the magnetic field is plotted into the paper and the electric field is out this way, we're going to see a creeping wave go around, right around both sides and come back out. And you're going to see here's the wave, and notice here, what happens is the wave goes around the back, and when it gets to the back, it comes back out, and what we see coming out in this right region here is a wave that comes back around and will interact with the wave that goes back, producing a creeping wave. You see where the wave is, the scattered part, and then after the scattered part goes out, we see there the creeping wave coming around and being generated. Weaker, of course, but that'll go back. But it's an example of it. Okay? And lastly, we're looking at simulation of scattering by a cavity, and the phenomena we're going to look at is a standing wave. And here we have a frequency of 300 megahertz. The wavelength is a meter, and it's a 2.5 meter deep cavity, 1 meter wide. So there's a resonance here. The wavelength is the size of the cavity, and it all resonates very nicely. And you see the wave come in. And what we're going to look at later on is this is the how shall I say it, after this point, what we're looking at is the sum total of the wave coming in and the wave bouncing back. And you'll see the standing wave build up, and then you'll see it generate energy back in this direction, the standing wave in the cavity, and then in these last segment we subtract off the input wave so you can see what's happening over here. This is just the scattered part coming out, not the scattered plus the incident. It's a little more complicated. So we have the wave coming in, the positive, negative, and you see after a while the standing wave building up, and then after it builds up you see the burst of energy coming out, and so this cavity reflects back quite solidly. And now if we just subtract off what comes in, you see that energy is coming out of the cavity very efficiently and moving back. So cavities are a no-no.